Welcome everyone to another episode of Vision Basic. It's been a while since my last video, but I've been super busy working on version 1.1 of Vision Basic, and if you stick around to the end, I'll give you an update on that progress. But while you're at it, please take a moment to subscribe to this channel. I was originally going to cover a different topic than what you see in the title for this video, but since I thought the other topic might take a couple weeks to form into a video, I chose this topic instead. So this video is going to be about how to improve disk access speed in both regular basic and in Vision Basic. Now, this was supposed to be an easy video for me to do. I've worked with disk access for quite a number of years, but the further I dug into the topic, the more complicated things became. For starters, I learned that you can't really rely on the system clock of the C64 to help track how long it takes to save and load data. Apparently, the results will be highly inaccurate. Taking this in mind, it made me realize that you can't really use the system clock as a reliable timepiece if you are accessing the disk drive to any major extent. The reasoning? Well, the clock loses all kind of seconds during each disk access. And this inaccuracy is how I wasted a lot of time trying to see how long it took to fetch and store disk data using a variety of techniques. My timings were simply inaccurate. So I ultimately had to record disk access times with a stopwatch in my hand, and my eyeballs would dry out as I try not to blink in an effort to catch that exact moment when a test was completed. Such is life. Now, if you simply want to load a file into memory from within a basic program, you can simply use the load command like this. And you can also use the sys command to call either the kernel load routine to load a chunk of data off of disk, or the kernel save routine to save a chunk of memory to disk. But sometimes you want more control over how this data is pulled from disk, and you might want more control over how your data is stored back to disk. And that's why BASIC provides us with the get number and print number commands, and we have the input number command as well, but we're not going to discuss that command here. And I'm just going to say get number and print number. I don't know the official way to say these commands. Some people might say hashtag. I just can't even stand that word hashtag, so no, I refuse. I am not going to say hashtag. You won't hear me say it once, except the fact that I just said it. Anyhow, now it's bad enough that the 1541 disk drive is pathetically slow, and we all know that BASIC in general is slow as well. So it adds insult to injury when you try to access a disk file with BASIC's get number command. And the print number command isn't a whole lot better, but it can certainly output more characters at once. And as an alternative, you can pair the CMD command with the regular print command for better speed. And I think I wiped out the first line of my program, so I'm going to type new. And load it again, okay. Okay, well, I didn't wipe out the first line. Whew, okay. There was no line 10. So here is a program I've whipped up for testing purposes. It essentially copies the basic ROM out to disk and then reads it back, noting how long it takes to perform both tasks. It doesn't have all the critical stuff like checking the error channel and checking the reserved variable st. We're simply testing different access methods against each other, so those things don't matter a whole lot here. And we're using Vice, so I'm not expecting a random disk error to pop up anyhow. To do any kind of realistic timing of disk access, Vice needs to be set up with true drive emulation. But since I wrote this program before realizing how inaccurate the results were going to be, the results that get printed to the screen will be inaccurate. I chose not to modify the program and remove the timing feature so that we can compare the program results with the actual results using a stopwatch. And I'm going to briefly explain the different parts of the program. This is all just really basic stuff. No pun intended. Okay, line 0 here deletes our example file from a previous run if it exists. So we're going to create a file example 1 in this program, and when we run the program again, we want it to be deleted again and again and again, so that when we save the file, it'll end up in the exact same spot each and every time for more accurate timing purposes. So, and then we have key presses here and another key press here, and there's none at the end. Here we are opening up the file, example 1. We're actually creating the file. That's what the W is for. When you create a file, and this is a program file, by the way. I don't bother with sequential and all that kind of jazz. Most of the time I just stick with program files, even if they're not really programs. You know, to each his own. The W means to write, so we're actually going to create the file, and then we're going to take locations 40,960 to 49151, which is where the basic ROM is located, and we're going to output it to disk. We're going to copy the bytes and output it to disk. Then we're going to close the file, and then we're going to issue a time, which again is inaccurate, and then we're going to fetch the data back, and each time we're setting the clock to 0. And here in 210 we are opening another file, same one actually, but this time we're going to read it. That's what the R is for. And then we're going to read back every single byte. We're not going to worry about poking it to memory. We're just going to read the bytes back. The test does not really require us to poke to memory. We're just getting timing information here. And that's pretty much it. We're just reading it and poking it back. So there you go. Voila. And we're going to go ahead and run the program. So here we go. And we're going to speed things up with warp mode, because of the true drive emulation, of course. Okay, and go ahead and run it. Warp it. Oh, that was the deletion in progress. And now we're going to run it. Or save the file. Sorry. And then we're going to press the key again, and they're going to read it back. And you probably won't see the little flashy light in the corner. And as you can see, it reportedly takes 56.283333 seconds to copy the data to disk and 65.2666667 to read it back. In actuality, it really takes about twice that long or longer. Using my stopwatch to time a real C64 connected to a real 1541 disk drive, the results ended up being about 137 seconds to save the data, and about 114 seconds to read it all back. Yikes. Of course, those who lived with cassette drives are probably laughing at me right now, because I've never used one, but I know that the wait times for a cassette drive, it's like killer. It's like you could feel like your wrinkles are forming on your skin as you age, waiting for cassette program to load. Now, believe it or not, though, these emulated values are very close to the values produced on real equipment. So if anyone thinks that emulation is to blame for inaccurate reporting, it's not. Now, if we were to simply load these bytes into memory using the load command, it would take only 23 seconds. So our basic equivalent is taking about 5 times as long to perform the same task. One easy way to increase the speed is by using the Blitz compiler. But believe it or not, Blitz is only going to knock off about 1/4 of the duration. And Vision Basic only does a little bit better with this program than Blitz. But it's worth noting that Vision Basic comes out fastest in all the tests we're about to discuss. I'll show a table with all the results near the end of the video. The table will show how Blitz improves things, and it will also show how Vision Basic improves the situation. For now, we're just going to focus on regular Basic and how to improve things there. Okay, the first thing we can do to improve the speed is possibly the most obvious. Let's use the CMD command to divert printed text to our selected device, the 1541. And I'm going to list it again. And I'm going to go up to line 110, and we're going to add our little, add a colon and a CMD and a comma and a semicolon. And we're going to eliminate this here because we won't need it anymore. Note that the comma and semicolon here are needed to prevent a carriage return from being sent to the disk file. I found this out after a bunch of head scratching, so. Now, it's important to ultimately stop diverting text to the disk drive, so we need to do this with the following. And I don't know how many spaces. We're going to do print number 2, comma, semicolon, and a colon. And bring this back. Rain it on back in. And I'm just going to go over the lines again. Blah, 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 blah. And we don't need to run the second half of the test, so we're just going to put an end here. And now let's see what happens. And press the key. Oh dear. What did I do? I have made an error. Let's see what I did wrong. Oh, you know. Some people probably caught it. I did not. How embarrassing. You have to put the channel into the right after the command. Okay, now one more time. Let's run it. Press the key. We have a disk error. I don't know why. I think I probably messed something up. Let's close 2. What the heck is going on? Okay, we're going to try one more time. And warp it. And here goes. Alright. The value you see here is certainly a faster time, but the real time for this test is about 60 seconds to output the data to disk. That more than doubles the speed. So we're on the right track. But the CMD command doesn't work for getting the data off of the disk, only for storing. So what can we do there? Let's load another version of the program, since I'm always prepared with more than one version, of course. And we're skipping number 2 because number 2 was our CMD version, and I don't need to load that. Okay. And I'm going to delete some lines here because I want to be able to list the entire program on the screen at once, or at least a good part of it. There you go. Okay. This version of our program employs the machine language routines built into the kernel to handle the fetching and sending of bytes. One of the problems with the basic commands get number and print number is that they first have to tell the disk drive to either talk or listen before they perform their single task. After that task is completed, the default devices of screen and keyboard are reinstated as the listener and talker. This all results in a lot of extra communication going through the serial cable, and this slows things down quite a lot. So let's look at the program here, and I'll explain how we're cutting out the extra chatter. In line 10, I have some values placed into variables for the purpose of speed. We have CO, right up here, equal to 65490, which is the location for the CHKOUT routine, and we have GI here equal to 65508, which is the location for the GETIN routine. CHKOUT handles our printing to the disk drive, and GETIN handles our getting from the disk drive. These aren't actually the true locations for the routines, but rather jumping points to the actual routines in the kernel. Variable A here is the address where we can place the value we want to send out to disk or fetch the value that is incoming. This address is register 780, and it is tied to the accumulator in the realm of machine language. And in line 120, we place a value of 2 in register 781. This is the channel we have assigned to the open file, the first parameter of the open statement. In the realm of machine language, register 781 is tied to the X-index register. The accumulator and the X-index register act like variables in the world of machine language. That's the simple explanation anyhow. And we call the checkout routine in line 20 with an SYS 65481. The checkout routine takes the channel value we give it and pretty much tells the disk drive to start listening for the data we're about to send it in relation to the file we just opened on that channel. Doing this replaces the CMD command pretty much. So if you put two and two together, you'll realize that the CMD command essentially tells the device to start the listening process. In line 140, we are copying a value from the basic ROM and placing it into the register associated with the accumulator. This is the value we wish to send out to the disk drive. By calling the CHKOUT routine, right here, with SYSCO, we are then sending that byte out to become part of the file we are trying to create. And in line 150, we are calling the CLRCHN routine via SYS 65484, and this restores the keyboard and screen as our default devices. Notice that this is done outside of the for next loop. If we were to use the print number command instead of SYSCO, like we did in our very first program, both the checkout and CLRCHN routines would be called for each of the bytes we are trying to send out, since the print number command calls both of them each and every time. This means that both routines would end up being called over 8,000 times each, and that just keeps the serial bus extra busy. And that was a mouthful. As a little side detail, the video chip also steals time from disk access so that it can perform its tasks. But the only way we can get those cycles back is to blank the screen, which is kind of disruptive. Now, the downside with the technique presented here is that you can't print text to the screen while the bytes are being sent to disk. If you want to display some kind of progress indicator, for example, you could issue a CLRCHN after every 256 bytes sent out, then update your progress indicator by printing an updated percentage to the screen, and then call the checkout routine again to get the output flowing back to the disk drive. Vision Basic uses this technique when displaying the progress of saving a file to disk. Just remember to poke the channel number to location 781 before calling the checkout routine. Alright, moving on to the rest of the program. In line 220, we poke the channel value into location 781 again, but this time we are calling the kernel CHKIN routine. And this tells the computer that we wish to get our data from that channel and to make it the current input channel as opposed to the keyboard. So now we're telling the disk drive to get ready to talk. In line 240, we call the GETIN routine. I don't know who named these. Via the SYS call, right here. And then we peak location 780 to fetch the byte that was just sent over to us by the disk drive. The kernel GETIN routine essentially replaces the get number command. And there is an alternative, I think it's called CHRIN routine, but from what I understand, GETIN, I think GETIN is more direct. CHRIN will, if used for the screen anyhow, will flash the cursor and stuff like that. So it's just best, I think, to go with GETIN. And in line 250, we call the CLRCHN routine again to restore the screen and keyboard as the default devices. Okay, so what do you think will happen when we run this program? Will we see blazing fast results? There's only one way to find out, and we're going to do that. We're going to run it. How about them apples? And warp it. Deleting the, okay. Again, ignoring the values, the real times are 72 seconds for saving the data and 62 seconds to read it back. So this technique takes 12 seconds longer to save compared to using the CMD command, but we've almost doubled the speed for the loading part, so this is still very good progress. The reason I think that using the CMD command is faster is because now we are using two commands for output instead of one. And since BASIC is the slow beast that it is, two commands are often worse than one. So yeah, right up here we have the poke and the peek, and then we have the SYS. So there are your two commands. So at this point, I wanted to see if we could remedy that. By creating special machine language routines, we can use a single SYS call for the saving part and employ the user function for the loading part. I'll show you what I mean. We're going to load program 5. Wait, let's... Okay. Okay. List it. The machine language data is in lines 300 to 320, and it gets poked into memory early on in the program, in the lines you can't see right now. This machine language is relocatable, so if you wish to use it, place it where you wish. Well, I mean, in a non-volatile area, of course. Line 140 shows our special SYS call that handles outputting a byte to disk. Notice that we have a peek function as part of the SYS command. I guess I chose BO here as an acronym for byte out when naming the routine. It has nothing to do with body odor, I can assure you. Anyhow, we only have one command here, so we might be inclined to expect better results. And line 240 here shows our special user function. We don't need to supply a parameter for the function, except that BASIC requires us to provide one anyhow. So I'm just using a period in place of a 0 since it reads faster than using an actual 0. The user command works similarly to an SYS call, except that you get to pass a value back from the machine language routine. And this value gets passed back to the B variable you see here. So here too, we have eliminated a command in the hopes that we'll see some better speed. And I'm going to list through 190. And let's get a look at the start of our program. In line 10, we poke the machine language code to memory, starting at location 53200. There are only 19 bytes between the two routines I've created. That's actually quite small. Line 20 shows that the byte out routine starts at location 53200, and the byte in routine, BI, starts at location 53210. In order for the user function to work, we have to set locations 785 and 786 to point to the routine. So some simple math here splits the location in variable BI into high and low bytes. This happens in lines 30 and 40. This value here gets shoved into these two addresses. And we can, of course, run the program and see what happens. Warp it again. Press the key. And press the key again. All right. And again, ignoring the inaccurate values here, the time it takes to output all 8,192 bytes amounts to about 62 seconds, which is just a tiny bit longer than using the CMD command. No gains there. And it takes about 46 seconds to read all those bytes back. And that's our best time ever if we're sticking with just regular BASIC. We're talking about almost 2.5 times faster than the original routine. Now, Blitz also sees its fastest time ever for loading the bytes back to disk, taking only 34 seconds to do so. And again, I'll show all the stats in a table here in a minute, but first we need to go over to Vision Basic and see how things stack up over there. And here we are. I took the first program that I made for regular BASIC and modified some things to make it compatible with Vision Basic. There are no improvements here for the sake of efficiency though. So let's go ahead and run it. Okay, press a key. And warp it, and press a key. Now, don't get an impression here that these are blazing fast times. The true results for these tests are 95 seconds for the output routine and 82 seconds for input. This is really not impressive for Vision Basic, but it's still faster than Blitz by about 7 seconds for each test. I wanted to maintain full compatibility with the regular basic commands when I created Vision Basic, so this program still suffers from all of those extra talk and listen messages that need to be sent out over the serial bus. The magic happens when we start with the introduction of the CMD command, and we are going to load the next program in our list. And here we've made the exact same changes as we did with the regular basic program. We added a CMD in line 110 and a print number command in line 140. And we got rid of the, actually we don't need print or print number here in Vision Basic. Now let's go ahead and run it. Press a key, warp it. Okay, press the key in. We don't need that second test. Now I know it's kind of pointless to run these tests since the times are far from accurate, but notice how quick the output test supposedly took. That's not even possible on a stock C64 connected to a normal 1541 drive, unless you involve a speed loader of some sort. When I started to see results like this, and I mean, I've seen it go all the way down to like 2 seconds, I knew that something was up. And this is why I had to redo much of the work I had prepared for this video, costing me extra days and extra time. So the real result for the output test using the CMD command is about 34 seconds. And that's about 5 seconds faster than using Blitz and almost twice as fast as regular basic. So from here, I moved to the SYS variant. Load our next program, and I just put the V's there. It's kind of like Blitz. The V is not a normal part of, you know, compiled output in Vision Basic or anything like that. I just thought it would be cute. I don't know. I wanted to differentiate between the different programs. You know, which programs went to which, you know, basic or whatever. And we're gonna list it. Now we could use SYS calls from within Vision Basic, but there is a little bit of overhead involved when using SYS, so a JSR call works just the same, but without the overhead. So here I've just set up some tags in lines 10 to 30, or you can call them labels if you will, and these tags will call their respective routines via a JSR instruction when issued elsewhere in the code. They're simply treated as user-defined commands. I had to get creative with getIn because you can't start a tag with the basic keyword get. So that's a 3. It looks like a backwards E though, so it's okay. We'll survive. Here's the char out tag, getIn, checkout, CHKIN, looks like chicken, CLRCHN. That's how I pronounce them. I don't know if there are official pronunciation guides for these, but if you know of any, you can let us all know in the comments. And when executed, the real results are about 30 to 31 seconds for the output test and 23 seconds for the input test. It's important to note that the 23 seconds hits the baseline right on the head when you compare it with actual loading the data with the load command, which also takes 23 seconds. When putting BASIC up against Blitz and Vision Basic, only Vision Basic can hit that mark. We're already using a couple direct machine language instructions to help speed things up a little, like the LDA in line 130 here, and the STA in line 230. But we still have the overhead provided by the for-next loop, and the results are still impressive. And if we get rid of the peak in line 120, this peak here, and substitute something a little faster, we can shave off a few more seconds for the output results, so let me load up that version into memory. So now we've eliminated the peak command, but notice our for next loop that starts in line 120. I bet you didn't know that you can do this in Vision Basic. Here we are setting up a pointer that will be updated by the next command. So instead of a variable equaling a value from 40,960 to 49151, we're allowing locations 251 and 252 in 0 page to take on that role. Since Vision Basic leaves these registers alone and the other two that follow them, 253 and 254, we can freely use them without issue. I wouldn't use this technique with other 0 page addresses because your loop might do some wacky things. I'm just saying. These changes for the output routine here knock off 5 more seconds, bringing the output test down to 27 seconds, which is only a few seconds more than the input test. And both results are awesome when considering the slow speed of the 1541. I don't know offhand how long it would take to save 8K using the official save routine of the kernel, but since saving is typically slower than loading, I'd say that 27 seconds is likely on par with using the save routine, or pretty darn close. So let's show all the results in a table now and see which techniques work best for BASIC, which techniques work best for Blitz, and which techniques work best for Vision Basic. Notice that I ran some tests where I tried using actual values for the CHKOUT and CHKIN routines to see if Blitz might run faster using real values instead of variables, but there were no speed gains. It actually slowed the results down a little. The results in regular BASIC were insanely worse compared to the results in the line just above. And now, let's highlight our best options for each scenario. So if you wish to stick with regular BASIC and not run your programs through the Blitz compiler, it seems that using the cmd command is your best bet for saving bytes out to disk, and using the user command is the best option for fetching bytes from disk. And these seem to be the best options if you're compiling your programs with Blitz as well. And if you're using Vision Basic, which consistently produced better results in all variations, I'd suggest going with the tags and using them as user-defined commands, as shown in the most recent program I loaded, which is right here. Okay, so there you have it. How to improve your experience with the get number and print number commands or their equivalents. I hope you all find this information useful. I really do. And before I go, I'd like to update you all on my progress with Vision Basic 1.1. Unless I go nuts and start adding more improvements and features, I'm pretty much done with all the improvements and features you'll find in Vision Basic 1.1. I still have some minor things to do here and there, and I need to make sure I haven't broken anything. And there are a slew of other things I need to do before the official release. I'm aiming for the 2-year anniversary mark, the official launch date for Vision Basic. I hope I can hit that mark, and I'd love to release it before then, but I still have many things to do behind the scenes. But I'll give you an early preview of a few of the enhancements right here in this video. I plan to do a release video that will outline all or most of the improvements and changes, so I don't want to share too much. I gotta leave something for the video. One of my goals has been to make the assembler part of Vision Basic a little more friendly to those who like to program in assembly language. So here are some things to look forward to. You will now be able to set the starting address for code using the familiar asterisk and equal sign like so. So here we go. Equals, nope, equals 49152. Unlike some assemblers, you won't be able to use this to set multiple starting points for code sections. I just wanted to add this form of notation since you see it in almost all assembly language programs. And we're going to type further. Let's type this. And you will also be able to set up tags or labels using a format similar to that found in assembly language. Now, you can't simply type a label on a line like you can in the assemblers because Vision Basic will see the label and treat it like a user-defined command and will want to execute it. So this is not going to work. So what we do The most logical thing I could think of to make this work was to use our little asterisk friend again. So we'll just add that to the mix. Right there. Now, I know that these aren't huge improvements. Again, I'm just trying to improve the feel of things for those who like to program in assembly. You can write entire assembly language programs in Vision Basic. And let's just run it. Voila. And one last thing I'll let slip out. Load our previous program. Check this out. I'm going to go up to line 130. And we are going to eliminate that. And voila. Say what? Where did the LDA go to? Well, the PK now becomes a parameter that is passed on to the accumulator. It makes the char out routine somewhat resemble char $PK, like you would in regular BASIC. And there's more to it than that, but I'm going to stop here and let that digest. This here is similar to a user-defined command, but meant for assembly language. Cool, huh? And now we've reached the end of the video. As usual, I thank you all for watching. Please like and share my video, and definitely subscribe for more similar content. And make sure to visit visionbasic.net